I want to recap where we were. And we're slowly grinding our way to understanding a gas in a box, okay? And we've made some progress by identifying kind of the things that can define our box of gas. And it's a pretty simple list, right? Let's just remind you of the things. So we have a box here of indiscriminate size, just some arbitrary box. The idea of this box is it's completely sealed. All right, there's another term for this, and I'll mention this later. We'll bring it up. Will it let me write? Yeah, there we go. This idea of the walls are completely sealed. All right, that means nothing can get in and out. Energy, particles, nothing. All right, the box is completely sealed to the environment. All right, the term we often use for this, and I'll mention it again today, is called a closed system. All right, it's completely closed to the outside environment. All right, and the only thing that we can really measure about this box, but it turns out that's all we need for the most part, is the volume of the box, the number of particles in the box, or the number of moles, however you would think of it. It's the same concept, just different unit. The mass of the particle. These are you can think of these gas particles as billiard balls. And billiard balls have some sort of momentum or kinetic energy. Kinetic energy momentum is defined by a speed, a velocity, and a mass. So you got to have a mass, right? The mass determines kind of how much momentum the object has. And then we have to specify with some property, which we haven't really determined yet, we will today, something that specifies how much these particles are moving in the box. Okay? They could not be moving at all, right? They could have zero kinetic energy. They could be moving, 99% of the speed of light. They could be relativistic, right? They could be any speed, right? But we need to have some property that specifies, right? We need to measure something that specifies kind of the speed or the velocity distribution of our balls, right? And then we talked about this a little bit. And the point was that tracking the velocity of each ball is not very useful. And the reason why is very simple. If you have two balls come together, each with different velocities, and then they bounce off of each other at new velocities, the sums of those velocities aren't necessarily conserved. So if the second ball comes in at v2, the first ball comes in at v1, the sum of those two velocities will not be the same as the sum of the final velocities of those two particles, especially if they're different masses. And Newton realized this. This is a well-known result. Velocity is not conserved, right, in the sense that the sum of all of them is not the same always. But what he does realize is that the momentum is conserved, right? If you multiply the velocities of each of the balls by the mass, then sum over all the momenta, that sum never changes, right? Even still, if you square the velocity, so you have mv squared, that's also conserved as well. And we identified that term mv squared times 1/2 as the kinetic energy of the particle. All right? So ideally, if we want to know something about the motion of these particles, we need to measure their energy. All right? The energy specifies how fast they're moving. Okay? And so the way that we kind of correlated this, or kind of put it all together, is that there's a third variable, the total energy of the system, U, which says something about the total kinetic energy of all the particles, right? All the particles are moving at different velocities. Maybe they're all moving the same. Who knows? Some velocities. The total energy, the total kinetic energy, which is the sum of every particle's kinetic energy, is always the same. Okay? There's always going to be, that sum is consistent as long as the energy is constant. Right? And the energy of this box has to be constant because it's closed. There's no way for energy to escape. So the total energy is also conserved. Okay, so there's this number U that we could maybe measure, that's measured in joules, right, in energy units, that specifies something about how fast these particles are moving, right? The higher the U is, the faster they're moving. The lower the U, the slower they're moving, kind of as an aggregate. Okay, and so, but the problem is, we kind of want to measure U, right? The box itself has defined energy, and we want to measure that energy as a function of the things that we can measure. Right? U is really hard to measure, right? Because there might be a mole of particles in here. Right? There might be 10 to the 23 particles in here. And in order to measure the total energy of all of them, you got to go to each one and ask the question, what's your energy? Then you have to do 10 to the 23 calculations. And so that's a really bad variable to put in, right? What we really want to do is get the energy of the system out such that the energy is a function of the easy variables to measure, right? Which is the volume of the box. All we have to do is put a ruler next to it. And the number of particles in the box. That's easy, right? We can weigh the box, for instance. Or we can feed the molecules in ourselves. We know exactly how many we put in. So ideally, we want to come up with some function u that specifies the total energy that's just a function of the other variables. But the problem is that v and n doesn't give us any information about the energy, right? Because we can have a box with the same v and n where the particles aren't moving at all, or particles are moving extremely fast, right? So there has to be another variable that we put into this energy function. It gives us the energy that tracks something about the speeds or the excitedness or the energetics of the particles inside. All right, we haven't identified that extra variable yet. All right, there needs to be one more variable that we need to add that will allow us to kind of track how much energy is in the system. All right. And at the end of class, we kind of talked about this briefly. I want to now return to this. Is that let's imagine now that this box only has 11 atoms in it, 11 particles. Okay? And we're going to set this problem up in a very simple way. So here's our box, and each of these little circles is an atom. We have an atom in the center with +2 charge. And it's on either side are atoms or particles of -1 charge. Okay? This is just an example. And then these are subsumed, they're to attach to the center atom are 4 neutral atoms. Right? These are zeros. Right? So these are uncharged, just boring old atoms. And they're attached with springs. Okay? So the atoms they all vibrate together, and they're all attached to each other. Okay? So you can think of this as a big kind of octopus kind of looking thing, molecule. All right? And then we have to ask the question, well now, if we look at this box, if we look at the motions of all the atoms, what kind of motions are there, right? How do the atoms move? And there's a couple of ways to approach this problem. One way to approach this problem is actually straightforward, but difficult to visualize, is we treat each of the atoms independently as if they can move in 3 dimensions, right? So each of the 11 atoms is an individual ball, and they can move independently, all right? They might be vibrating, they might be moving. Right? So each one of these has a coordinate, right, in the box. So let's just pick this one, for instance. We'll call this atom J. It has coordinates x sub j, y sub j, z sub j. Okay, so it's somewhere in that box, and it's moving around. Okay, it's some velocity. Right? It's got some motion, right? And so each one of these atoms also has 3 coordinates that define it, right? This one's at a different position, this one's at a different position, and so on and so forth. Right? So how many possible coordinates are there for the system? Well, each atom has three coordinates, x, y, and z, and there's 11, so there's 33 total coordinates. Right? So in order to track all of the motions and the energies and stuff, we need to watch these atoms move. And the plot that we make, or the energy, how we measure the energy, is a function of 33 different variables. Well, that's a real pain in the butt, right? Imagine now you had a mole of atoms in there. Right? You would have 3 times a mole. You'd have 3 mole of coordinates. Your function would be x, y, z times 10 to the 23. Right? That's an insane number. Okay, so we can't obviously track each atom independently. All right, so what we're going to do instead is imagine this box the way we actually measure it. All right, we're going to look at this box, right? You can't actually see atoms, right? But you could see motion of atoms if that motion isn't random. Right? There might be some motions that are conserved, that show up macroscopically. What do I mean by that? So imagine you have this box that's this size, okay, and you're looking at it, and these atoms are moving around at normal speeds that atoms move around. Okay? An atom moves around 1,000 meters per second of room temperature, okay, give or take. All right? And the diameter of an atom is only about an angstrom, about 10 to the minus 10 meters. So you can quickly calculate how long does it take for an atom to move by 1 unit of atom length, right? How fast does it take, how much time does it take for an atom to, say, move from here to here, right? A little vibration. And it's really easy to calculate that this is around a femtosecond, 10 to the minus 15 seconds. So these atoms are moving 10 to the 15 times a second. They're vibrating 10 to the 15 times per second at room temperature, at an energy equivalent of room temperature. So obviously you can't see them moving, right? They basically look like this. Right? But imagine now, for instance, that all of them are moving collectively in such a way that gives you a net motion. So here are some examples. One of the examples is what if all of the atoms move away collectively from the center? Right? So you have this +2 charge. Imagine we're sitting on that atom, looking at the other atoms. Right? We're in the frame of reference at the center of the box. We're sitting there. We're watching all the atoms move around us. Okay? Einstein tells us that when we sit there on the +2 atom, we can represent it as if it's not moving, and everything else can move around us. It's the equivalence principle. And what you see is that you see all of there are different types of motions that the atoms can do. But one of them that you'll see is that they all move away from you. Right? Imagine you're in the center of a sphere and you're surrounded by this sphere of atoms. And what's happening is the sphere is breathing. It's moving out and in collectively. Right? And when you think about that, well, what is happening to the physical dimensions of the gas, this little ball of atoms? Well, the volume is changing, right? Think about it as instantaneous. The volume, the atoms are pressing away from the center, and they're pressing against the edges of the box. Right? Eventually, they're going to hit the box, right? Maybe bounce off. Right? So this motion induces a change in volume. Right? And we would see that. Right? We would see on average, these molecules are going like this on average. You can't really see them moving independently. But what you do notice is that they're pushing against the walls like this. Because you can maybe feel the pressure of them, right? Maybe you can sense the pressure of them hitting the walls. Right? So there's these motions that allow this gas to expand in the volume. Okay? Imagine that you didn't have these. I'll show you an example of this. We'll have a simulation of it. Imagine I didn't have these springs. They're just independent. Right? And I start in the center. They're all clumped up together. Right? You have this little clump of atoms in the middle of this box. What happens? Well, these atoms are going to move around randomly, but there's going to be some motions where the atoms push apart, away, kind of spherically, away from the center. And eventually what you're going to find is that even though they're moving very, very rapidly, in the end you're going to see that the atoms fill the box. Right? They're no longer centered in the middle, they're diffused out into the box. Right? And so even though the atoms are moving faster than you can see, you can still measure the result, which is that the volume has changed, right? They filled the box. You started from a small little droplet, and it's expanded to fill the entirety of the box. Right? So there are some motions that you can observe changes. Right? We call this one, the ones that create changes in volume, mechanical work. The reason why it's called mechanical is those atoms are literally pressing against the boundaries and applying a force to them and causing the volume of the box or the volume of the region to expand. We call that mechanical work, the idea of pushing something in distance. Right? They're pushing the sphere of themselves away from the center. All right, so there are some motions that we observe that average out. Let's say all move around randomly. We watch them for seconds and seconds and seconds. There are a set of motions that lead to an expansion of the volume. They fill the box. All right, what are some other options? Well, we also have these -1 charges and this +2 charge. All right? And if we think about the dipole moment of the system, which is the net charge in a given direction, the kind of the unequal distribution of charge in space, well, there's an unequal distribution of charge in space along this axis, right? We have +2, -1, right? So there's a dipole pointing in this direction, from -1 to the +2, but it's canceled out equal and opposite by the one on the other side. Okay, so from this orientation, there's no dipole, right? All the charges are canceled out. The -1's canceled out by this one on the other side. But there's a motion where these can wag like this, right? Where the ones, should I draw it? The the minus 1 atoms can push either collectively up or collectively down like this, so that the 2 is in the center, and now you have these minus 1s kind of at an angle like this, right? Like this or this, right? Like that. And when you do that, the dipole changes. Because now if you have, say, the minus 1 is here and the other minus 1 is here on the edges, on the corners, you have a net dipole in this direction. The dipoles no longer cancel out up down because you have minus 2 charges down here and not up here. Okay? These 2 were down here. So there would be a net dipole in this direction. Right? So you can have those motions, and so if you have a charge asymmetry in your box of gases, you have some -1 charges and some positive charges mixed around, you'll end up noticing that that gas can conduct electricity. Right? You run a voltage through it and electricity will pass right through it with a current. What that means is that the system exhibits a net dipole moment, which allows it to conduct. Okay, so even though there's a bunch of random motions, these things are moving together, if you have charge separation, charge asymmetry in your gas, you can conduct electricity. You can do what's called electrical work. Right? We won't really focus on that so much, because a lot of chemistry isn't about electrical work, but this is important, say, for plasmas. Plasmas is the most important force. It's the electrical force in a plasma. Right? So then you can think about, well, what are the other motions? Right? Well, there might be some other ones. But what you find is that the vast majority of the rest of the motions don't exhibit any changes to the variables we can measure. Right? What are the things we can measure? We can measure N, V, and in this case of electricity, we can measure something about the conductance of the material, polarizability of the material, which we're not going to worry about so much. Right? But in terms of an electrically neutral environment, the only 2 things that we can measure really are V and N. So there's going to be a series of motions in this gas, options, ways that the gas can move that don't change the volume and don't change the dipole. Right? You can kind of think of these as rotation motions, right? Where each of the atoms is exchanging with the other one in a circle. Just kind of move in a circle like this. And there's one also where it goes the opposite direction as well. Right? These motions, the molecules are always moving, the atoms are moving in this way, but they all average out. They don't change the variables we can measure anymore at all. Right? So there's a series of motions that we can measure changes to our system, volume and electrical work, for instance. Right? But there's a large series of motions our gas can do that we observe no changes at all. We know the gas is moving like that, but all of those motions, if you will, are just kind of averaged out, and they're canceled out in an averaged way. Right? There are many, 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 many atoms, tens and millions, billions, trillions, and most of the motions look like this. They don't really change the system, and so you can't really observe them. Right? So we can kind of think of this third class of motions as kind of hidden motions. Right? They're things that the gas is doing, but we can't observe any sort of macroscopic change. Right? Our volume meter, our conductance meter, our number counter, they're not changing at all, but the system is exhibiting these motions, right? Part of the energy is being used to do this. Okay, so here's the issue. Right? So if we think about it, right, we have nothing, N is never changing because the box is sealed. N can't change, although the numbers are fixed. Right? So what are the only things that can change? Well, the volume can change, right? And then the dipole can change, but we don't worry about that, right? We're not worried, that's only for negative and positive charges. Right? And that's it. There's nothing else. It's the only things we can measure. Except there's this last variable here that we haven't determined yet. Right? Which says something about that tracks these motions. Right? We have to have something that tells us how excited the gas is and how it's moving. We have to have something to track that, which is this remaining thing. Right? And so if we think about it, this motion affects this variable. This motion affects some electrical variable, which I haven't written. And N never changes because no molecules can leave the box. Okay? So what that means then is in terms of the energy, these motions must have something to do with this other variable. Right? This other variable we haven't defined must specify the kind of collection of these hidden motions we can't measure that are all averaged out. Okay? And the more of these we have, the more energetic the system is, the faster it's moving, and the more hidden motions it has, the larger this number should be. Okay? It's got to track something about how many of these hidden systems how much the energy is being partitioned into these motions that you can't observe because they're averaged away statistically. Okay? So we have to define what this variable is. And one of the big goals of this class, first of all, you know what this variable is. You've heard about it. You learned in Gen Chem. Probably not obvious what it is yet. This variable is super important, right? And it will define most of the things in this class. So what I want to do today is define that variable. Okay, so let's just briefly chat. Let me zoom in a bit. Let's just briefly kind of get ourselves into position to really define that final variable in our function. Okay, and so the idea is that in our box, there are motions that fill the full volume of the box. Right? Those are those mechanical motions, right? The box, the atoms moving away from the center. Right? We call these, there's a term for them. One, we call it mechanical work, right? The mechanical motion of things moving in space. Another thing that what we'll call it in chemistry, and we'll define this better on Thursday, is called PV work, or pressure volume work. In the case of the box, that makes a lot of sense, right? Because our system is expanding in volume with these motions, and eventually it's going to hit the edges of the box and apply a force to the box, and literally what we call atoms hitting the edges of the box when they're filling the box is what we call pressure. The net force of all those atoms hitting the walls is the pressure, right? So there's this type of work called PV work, which is how the system defines the volume and defines the pressure for the system. And that's just literally mechanical motion of the atoms pressing against the walls of our box. Right? And then if the system is not electrically neutral, I don't know, what's the opposite of neutral? Electrically polarized or biased or something like that? Right? It's charged. Then we have some electrical motion, electrical work. Which allows us, basically, that's the flow of electrons, right? That's the flow of electrons and charges through the box. Okay. Right? And then that's it, right? The box is sealed, so the molecules can't exchange, right? The atoms can't leave the box, so there's no motion along what we'll call chemical work, which is changing the moles of things, chemical work. We haven't gotten there yet. Right? We're assuming that the box has a fixed number. So we've accumulated PV work and this electrical work, right? And then everything else is left over. Everything else is averaged out in this box. So all other motions exhibit no macroscopic change or macroscopic changes. Okay? And we have a term for the energy content of these motions, right? You can imagine that there's 1,000 different ways for the atoms to move in this box. And let's say 2 of them are PV work, 3 of them are electronic work. The rest of them are these average motions to just average out. right? And they're going to have some energy content, right? Because the molecules, the system will occasionally be in these states that average out, and they're going to have some energy, right? And the energy content of this averaged motion, all these motions that we can't measure but are always there, this is called entropy. The label that we often use for entropy, let me change it a different color, is S. Why it's S, I have no idea. Because there's no S in entropy. Okay, so entropy, which we'll spend a long time on entropy because it's an important concept. First of all, it tells us something about our box, right? Now we have this variable S that tells us something about all the energy content of all these motions we can't measure. Right? We have something that changes V, something that changes electrical stuff, and then we have everything else jumped into S. Okay, entropy. Entropy, right? So what that means is that our function, our energy function for our box, so I'm just going to draw the box really quickly. We have this box, we have our little atoms in it. Now, forgive me that they're all different sizes. I want to assert that they're all the same size. Right? And they're all moving in random directions. Right? We can always describe this box with a total energy, right? The total energy of the box, right? Which is the total energy, and I'll just write that below. The total energy of this box can be represented as a function, first of the volume, right? That's the part of the energy of where exhibits the, right? As V gets bigger, the system has to exert more energy to fill the box, right? To fill the space. So V measures something about the PV work. That's how we measure volume. There is, of course, the number of particles in the box. Right? I'll just say that there are n atoms in this box. Right? There are n atoms in this box. Right? And then finally, the thing that tells us about the energetics, which are everything that N and V doesn't track, is S, the entropy. Right? So the entropy is some number that somehow tracks the number of these kind of average motions. Right? Everything gets accumulated into this one variable S, entropy. And what we're going to spend a lot of time talking about entropy. I'm sorry, it's really hard to see the ink. I apologize. I have to fix my colors for this room. Make it a little brighter. Okay. So our box, our sealed box, can be represented by three variables: moles, entropy, and volume. Okay. Now, you may ask the question, that's a really good question to ask, how do you measure entropy? All right, so we haven't quite gotten there yet. We have to come up with a way to define entropy. All I've said is that it measures something about these random motions that all average out. All right, all these motions we can't observe, but we know they're there because they contribute to the energy. They're all average out. We don't notice any changes in our macroscopic variables. Okay, so what we're going to do today, or as we push through this, is to come up with a definition of what entropy is and what it measures and what its behavior is. Any questions so far? Okay. Now, you may ask the question, for instance, what are some other things, right? I've mentioned PV work and electrical work. What are some other types of motions that maybe you can see macroscopically in your gas or your fluid? Right? There are many, right? I've just mentioned some very simple ones, right? This is a very, very simple box, right? But for instance, what if you, for instance, have a box that has an opening and a closing, and you flow material through that box? Like say, like a like a faucet, right? You have water coming into the faucet and out the faucet, right? What are the macroscopic variables of that flow? Well, the atoms define a volume, right? That tells you something about how big that flow is, right? The number of moles, obviously, how much material is moving through the box. And you can think of these atoms, again, all of these atoms in this flow, or a liquid or a gas, however you want to think about it, are all moving randomly, still moving randomly through there, so they have an entropy. But there's another macroscopic value you can measure, right? That's the flow velocity. Right? You know that the gas is moving, or the fluid is moving from the left side of the box to the right side of the box. So there's this net motion, macroscopic motion of the fluid from the left side of the box to the right side of the box that doesn't average out. Right? All the molecules are tumbling and colliding with themselves in this fluid, but they're all the net motion is still from left to right. So there's also maybe, for instance, a flow velocity you measure. And the study of flow velocities and flow in fluids is called hydrodynamics. Right? If you're a fluids person, you've done chemical engineering, I'm sure you've learned about flow and diffusion. Right? Diffusion and flow are measurements of macroscopic variables of net motion from, say, geographic motion, right, from left to right. Another good example is elasticity. Right? If you take your box and stretch it, right, how much energy does it take to stretch that fluid? All right, let's think about it differently. Let's say you have a gas or a fluid, and you want to compress that fluid, right? You want to crush it, and maybe you want to spread it out, right? And so if you can think about this process, again, in this fluid, all the atoms are moving randomly. But as you start to apply a force, an external force to that, you might compress the fluid or stretch it, right? And there's this net stretching motion, this deformation, right? Even though the molecules are still moving randomly in the liquid, they have this net motion as they start to compress. Okay? Right? And then also you can think about strain, right? How much energy does it take to stretch a fluid or a material until it breaks? Right? The study of those things are called rheology. Right? Rheologists and hydrodynamics people have they start from this exact principle that we've started with, but then they say, well, let's add another macroscopic motion to the system, a flow or a strain or an elastic motion. Right? And then in the electrical case, there are tons. Right? One, we've defined something about the conductance. If the system has a net dipole, you can conduct electricity through it. But as we'll see, there are materials that have net behavior such as magnetism. Right? We'll see that, and when we talk about phase transitions, that some materials show a net magnetic dipole. They are attracted to magnetic to other magnetic materials. Right? And that is also going to be a parameter that shows up in here, something about the magnetism. A net macroscopic fluctuation of the system that remains macroscopically after everything averages out. Okay, so there are lots of different ways to do this. And one of the things that we're really going to focus on in this class is we're chemists. We're going to want to start to think about systems that have multiple components, right? Two molecules. Maybe they're in equilibrium with each other. Maybe one forms the other. Right? Maybe they are attracted to one another. Right? We'll have to think about the energetics and how the box evolves if, for instance, two molecules can transform into one another. Right? That'll be really important for chemistry. Right? And then we'll start to see parameters that are related to N. The box will exhibit net changes in N that we can observe because we're reacting one molecule to form another. So the ends are changing. Okay? That's chemical equilibrium. All right, we'll get to that. So the idea is that every system can be represented by this function, but how the system is defined and how we apply external forces to it or constraints determine how the system evolves. There may be other things that appear depending on how we evolve the system or the box, but in the end we can describe any box with these three parameters. V, N, and S. Okay, so now you can kind of think of this as the prelude to the class, because now I'm going to hit to the defining point of this class. Right, now what I want to define now is our box. I have a very generic box that I've talked about. All right, and I just want to be a little more specific about the chemistry box, the box we'll use to create chemistry, and think about the energy content of chemistry. All right, and the choice of box that we're going to use, we're going to, so I'll call this, I don't know what to call this, we'll call this postulate 0. So a postulate is something we're going to assume to be true. All right. A system, which by system I mean a box with stuff in it, certainly we could talk about a box without stuff in it, but we're chemists, we don't really care about things that don't have things in it. Is called a thermodynamic system. If all microscopic flux motions, right? Those are those little motions we talk about, average out such that they could be represented by a single time-independent function. What do I mean by that? What I mean is that a system is what we call a thermodynamic system if the state that it's in never changes as a function of time. Right? Okay. What that means is basically that a function that has total energy U, which can be completely defined by N, V, and S, is thermodynamic. Okay. Now, what would be a non-thermodynamic U function? Well, what if, for instance, here's a counterexample. Now, maybe not a counterexample. Yeah, I guess. Right. What if, for instance, U is defined first by the initial number of particles, the initial volume, the initial entropy, and then also defined by how those numbers change as a function of time. So the time derivatives of say, V with respect to time, dN with respect to time, and ds with respect to time. Right? These are the time derivatives. Right? This is how these change with time. Time dependence is not a thermodynamic system, a thermosystem. Or let's say is one. It doesn't matter how you write this. It's not one if any of these time derivatives are not equal to 0. All right, so basically a thermodynamic system is one where the time dependence has gone away. Okay, let me give you an example of something in this room that is not a thermodynamic material. Let me explain. So what is a thermodynamic material? Well, the gas in this room, if I sealed the door, it's probably better than if I sealed the door. The gas in this room, the air in this room forms a thermodynamic system. Why? Well, if the door is sealed, N is not changing. We have a fixed number in here. V has not changed because the room has a fixed volume. And we're going to assume that the entropy is not changing because we're not moving any energy out in and out of the system. Now, that may not be true because I'm here sweating. I'm exuding heat. So I might be heating the room up a little bit and exciting the molecules, but right, this would be a thermodynamic system. If I come into this room, the idea is I come into this room, same conditions every single day, same volume, same number of particles or pressure, however you want to think about it, same energy, then the total energy of the system is fixed in time. Right? It's the same every time. Energy is conserved. Okay? If we have something that whose energy depends on how fast the volume or the number of molecules, the entropy changes as a function of time. So for instance, if I start with a hot molten material and I cool it down, right? Which is something we'll find has something to do with the entropy change with respect to time. Right? We remove heat from the system or energy from the system. And I do it at some rate. Okay? When you do that, you get some material out. Eventually it cools and you get some material out. Now you go back and do the same thing again. You take the same amount of molten material, the same initial conditions, but you cool it faster. Maybe you quench it in water. You get a different material. In fact, you get that with this. That's how they make glass, right? The kind of glass you get, right? They all types of glass, or these glass all start with, right? There's just silicon dioxide, just sand, SiO2. It's molten sand, right? And depending on how fast you molten it, you shape it, right? And then the thing that determines the strength of the tensile strength of the glass, the transparency of the glass, all of that depends on how fast you quench the heat. I don't know if any of you guys are glass blowers or have seen this before. But you get different types of glass depending if you douse it in water immediately after the heat, or if you let it air dry, air cool a little bit, and then douse it slowly in water. Right? You get a different kind of glass. Right? What that means is that the final state of the glass after you cool it, right? Here's the initial state of the molten glass, and these are variables that tell us about how fast we're cooling it to our final state. If the material and the energy that you get out is a function of the time, then that material is not thermodynamic. Right? Glass is not thermodynamic. What does that mean? Well, we'll look at the consequences for that. But what it means is that glass is not a stable material. In fact, you can predict, and it's a very, very long time, but this pane of glass has some time scale for it to melt. This pane of glass will never last for eternity. Eventually, this glass will melt. Now, it might be 10, 20 billion years from now, but because the system is not thermodynamic, and as we'll see, systems always want to tend towards a thermodynamic state. This will eventually melt and dissipate, the glass. Glass is metastable. Right? There's lots of different materials like that. Right? So we have to do a discrepancy. We have to distinguish between what we call thermodynamic materials, thermodynamic states, and non-thermodynamic ones. Okay. What we're going to find is that, again, it's a very, very simple argument. A thermodynamic material has no time dependence. All right? You fill your box of a given volume with a given amount of entropy or energy, a fixed number, you get the same energy out every single time you do it over and over and over again for all eternity. No time dependence. It has nothing to do with the path you take to fill that box. It only depends on what you put in the box and how big the box is and how much energy there is. Okay? That's what we call thermodynamics. Right? That we don't have to worry about time. We don't have to worry about the path we take to fill the box. It just matters how much you put in the box, what's the size of the box, and how much energy it has. Okay, but of course the question you have to ask yourself is, do thermodynamic states even exist? All right, we'll have to think about that a little bit. And that's not immediately obvious, but what we'll find is that, and the problem set Rowan really works on this a little bit, is that thermodynamics is inevitable. Every state tends to a thermodynamic limit. Right? Every state, even if it's in a system if it's in a current intermediate state that's not thermodynamic, meaning it's dependent on time, there is a time scale for which it to go into a new state which is thermodynamic. All right? It will always tend towards thermodynamics, thermodynamic limit. How long that takes is a different question altogether. So what we can actually expand this a little bit is add the next postulate. And again, this is something we assume to be true, which is that there always exist states which states are N, V, and S for a given system, some arrangement of the atoms in the box, if you will, right? Called equilibrium states. That are completely characterized by U, V, and N. Okay? You could also write S, V, and N. It doesn't matter. Right? But if we know the energy of the system, we know the volume, and we know the number of particles in it, we can find out anything we want about that system, that box. Okay? And the important thing is that these are unchanging in time. All right? Now, what I have not said is that these states are not always achievable. For instance, the glass. Right? We've put the glass in a state that's not thermodynamic. What that means is that it will always want to tend to rearrange itself into a state that's equilibrium, where it's not dependent on time. But the glass is what we call a frustrated material, which means it takes a lot of energy or strain, whatever you want to think of, in order for it to have enough energy to melt, if you will, right? To go to a state that it actually wants to be in. Right? And so that material is not at equilibrium. It constantly wants to go to an equilibrium state, which for glass is a melted state, just a liquid, or a solid, a powder, if you will, right? Like sand. But it can't, because it actually requires a little bit of energy to go over it. So that's why, for instance, if you're in Arizona and you have regular single pane glass windows and it's 140 degrees outside, your windows melt, because you've given them enough energy to get over that frustrated barrier and start melting. All glass once tends to melt. It's just good glass tends to melt very, very slowly. Okay, so let's go back to our box and think about how do we find for our box what the equilibrium state for our box is. Okay, so let's imagine, for instance, that the way that I've built this box is I've put a little droplet of some number of atoms in a corner. All right, way in the corner. Just sort of like 10 or maybe a million atoms. They're all sitting really densely in the corner. All right, I want to know what happens to those atoms as that box evolves in time. When does it stop? Right? What's the state where once it starts to diffuse? Right? You can kind of imagine that little droplet's going to spread and fill the box. What is the state of the box when it's done doing that? Okay. So the way we're going to set this problem up is pretty straightforward. So I'll just draw it. So let me go ahead and go to the next page. So here's the problem, the basic thermodynamic problem. Right? And we're going to try to get this to chemistry as soon as we can. Right? We're pretty close. We just got to talk about the way to measure this box, and then we can start doing chemistry. All right, so the way I'm going to draw this box is instead we're going to do something a little different than what I did before. So again, imagine this is a 3D box. In the middle of the box, I'm going to put a small barrier called a piston. Oops, sorry. All right, I'll color it in. Oops. All right, so we have this little piston here. All right, and all a piston is just a divider that can move. Okay. All right, and so if we're going to set this piston up, initially so that it's closed. All right, so the initial problem, so we can define what the piston is, but maybe the piston, so we'll just define all the possibilities. Piston can be closed, which means that no heat, no energy, and no mass can move through it. No energy transfer, energy or mass transfer. It can be what's called adiabatic. Right? This is a term we're going to see a lot in this class. Adiabatic means no heat transfer. Right? So there's going to be no motion, no entropy, no heat. All right? So no energy transfer. Right? But maybe a mass is allowed to transfer. Okay? And then we're going to have what could be a diathermal wall. Diathermal means energy transfer. Right? That we can exchange energy across the barrier. Energy transfer, okay? And then we can also have an open wall or a porous wall. Right? Which allows everything to come through. Porous open. Allows both U and energy. Let me write that explicitly, I'm sorry. Allows both energy and mass transfer. Okay. So we can choose how we can choose how to set the piston. We can put a piston in, and then we can see how the system evolves with that piston. All right, but let's assume, for instance, let's first assume an initial condition, all right? So let's first assume a fixed closed piston. All right, what I mean by fixed is that you can't move it, okay? It's fixed in place. All right, and closed means you can't transfer anything from one way or the other. Okay, and then what I'm going to do is I'm going to fill each side. Basically what I've done is I've took the box and put it in and made two boxes out of it, right? That's all I've done. Simple as that, right? Now I have, instead of one box, I have two boxes. All right, and we're going to say that the initial conditions of the system, there's U1, N1, and V1. All right, so the volume, the energy, and the number of particles on the left box is N1, V1, U1. And on the other side of the box, we have U2, N2, and V2. Okay, so those are our initial conditions. All right, so we have initial conditions. U1, N1, V1, U2, N2, V2. Okay? And as I said, these three variables completely define my thermodynamic box. All right, and the questions that I want to target today, or not today, but maybe this week, let's say this week, because we're not going to have enough time to get through all of it today, is I'm going to ask two questions. All right? Question one. How do conditions change if I free the piston? Right? So it's still closed, right? No energy can transfer, no mass can transfer, but the piston can move. Okay. And the question, too, that I want to ask is what happens, how do they change? Conditions change if I make the piston porous. How do atoms flow? Right? So these are questions I want to ask. Right? So we'll worry about the second question a little bit later. Because we'll have to think about that. But right now we can think about N1 and N2 basically being fixed. But if the piston is free to move, imagine that the particles on one side are more energetic than the ones on the other side. They'll be exerting more force, PV work, against the wall than the ones on the other side are. And so the piston should move. Right? But the question is one, what direction does it move? And how the hell do I track that mathematically? And also, when do I know, as this piston moves, when does it stop? What condition does the box have to obtain where I'm guaranteed that the position, where basically the piston is stopped? Right? Because I can track the energies as this piston moves all the way to the other side and back. But where does it settle? Right? After this whole process is done, where does the piston settle? So unfortunately, we don't really have a way yet to track that. Right? All I've said is that the box is defined with these two variables, right? U, N, and V, each side of the box. And now when I loosen the piston, I'm allowing V to change. Right? The volume might change of each side because the piston will move. The question is, how does it move? How do I calculate how does it move? And where do I know the piston is going to be, where it's going to stop? Okay? It's a pretty simple question, but it's not obvious how to track that with the variables that I've given you. Right? Now, certainly we could measure it, but let's just see if we can predict it. So the question is now, is that when I free this piston, how do I know mathematically the position it's going to stop where we've achieved the thermodynamic state in equilibriums? Right? The state that's unchanging in time. Okay? The key to that is the entropy. Right? The entropy, which I haven't written down here, but as you know, entropy is underlying here. It's a part of U. Right? The entropy is going to tell us something about, the entropy is going to have a certain property which will tell us exactly, if we measure that property in the entropy, we know exactly where the system will stop. Entropy will tell us that. All right? Which allows us, so let's think about that. So let me take my box. Just going to copy it over to the next page. Right, and we're going to free this piston. Right, and what we want to see is what are the final values of U, N, and V for each side of the box. And so what we're going to do is we're going to track these variables. Right, and we got to track them to a certain point where we know that the value is stable. Right, it's going to move. It might fluctuate, but eventually it's going to kind of like settle into a nice spot. Right? And the idea is that we're going to track a variable and extremize it. What do I mean by that? Well, we're going to use a little bit of calculus. We're going to assume thermodynamics is reached. So a thermodynamic state is reached when one of the variables we can measure reaches its maximum or minimum value. Okay. So the idea is that if we have some variable, right? So let's just think about it in terms of time. It's not really the best way to think about stuff, but let's say at initially, let's call our variable x. Variable x. Don't know what it is yet. But let's say at initial time, our variable x is right here. So this is x of 0. Right, and this is going to fluctuate in time. Maybe it looks something like this. Well, it's not going to look like that, actually. It's going to be a function. Sorry, let me erase this a little bit. It's not going to overlap on itself. It's going to be a function. Right, so there's a couple possible ways that it can go. One is that it can travel, we can track something that travels a long time until it reaches a minimum. Right, so we have some minimum value. As you can see, this red curve, or this blue-purple curve, asymptotically approaches this yellow line. We could write this as x is infinity. Right, and the value at this point, let's say right here, for instance, right, the value at this point that we measure is a minimum, right? It's first the lowest value that the function takes, x takes. But the most important thing here is that the derivative is equal to 0, right? So if we look at dx dt, the derivative of x with respect to time at this point is 0, right? So it's unchanging. Right, so we've extremized this value, but we've done for the minimum. Right, so this value is changing in time, but eventually it starts to reach some value where it doesn't fluctuate anymore in time, and this is our equilibrium value of x. Right, so this is if we were to minimize it. Right, but there also could be a function that we could write that is maximum at that point. Right, so let's call that x prime instead. And let's say x prime starts at the same point. But as we track it, it increases. Right, and it increases. Let me make this a little more obvious so it's the maximum. There you go, right? So we have this point right here. Right, which is x prime. Right? And that's a maximum, right? The dx dt is 0 here, and it's a maximum. Right, so we have a choice. We could pick a variable that decreases in time until it reaches an asymptote, or we could pick one that increases in time until it reaches an asymptote. Okay? And it doesn't matter which one we pick, we just have to make a choice. And the thing is that by choosing entropy as the way that we're going to track this system, right? That's that variable that has something to do with energy. We're necessarily going, it turns out we're going to maximize this. All right, so let me define what entropy is now. All right, entropy is going to be the thing that we're going to watch. And the trick is that the thermodynamic limit, or the thermodynamic state, right, or where the piston ends up in the box, is going to happen at the place where the entropy is maximum. So let me write that out. Postulate 2. There exists a function entropy S, which is called the entropy. Which is a function of the energy U, the number of molecules, and V. That is well defined for all thermodynamic states, okay, the values of U, N, and V in a thermodynamics, in a system, are those, let me rewrite this. I just have to rewrite my text a little bit. So the values that we get in an equilibrium state for energy, number, and volume are those that maximize the value of S. What this means is that in our box, we have an initial state where the piston is sitting somewhere. Okay? Piston is sitting somewhere, and we let that piston go. And that piston's going to move, right? And as a function of its position, each position will have a different entropy. Right? We'll work this out next class. Each position is going to have a different entropy. And the position where the piston's going to end up is the one where the system's entropy is as high as possible. Right? Entropy, as we'll learn, is always increasing and needs to be maximum. All right, so what we're going to do is we're going to play around with, look at the energy of this function. The entropy of this function is a function of the internal energy, the number of molecules in it, the volume of each box. We're calculating the entropy of it. And wherever the entropy is maximum as a function of those variables, that's where the system will sit. So we always are guaranteed if we're measuring entropy at every little point in our system and we reach a maximum, then we know that that's where the system is going to land. And will stay there forever. All right. I have one more thing I want to say about entropy, and then we'll really start to tackle entropy and then think about energy next class. So I just have one more thing, and this helps us define what entropy looks like. Because what I've drawn up there, again, these don't really look very nice, right? They're kind of random and stuff. So entropy can be anything in this thing, right? So we really need to limit what entropy is and how it works in order to limit kind of what this curve is going to look like as a function of time. Right? And it's a really, really simple, entropy has very, very simple properties. All right, this is postulate 3. Or, yeah, I think. Okay. The entropy S of a composite system, what I mean by that is a system that has multiple components, like 2 boxes. So like a system with multiple separate components. Like 2 boxes put together with a piston. The entropy is a linear, continuous, and monotonically increasing. I'll define all of these in a second. Function of its variables. Okay, what does that mean? What does that mean? Okay, so let me define each of these for you really quickly. It just takes a couple seconds. What does it mean to be linear? Well, imagine you have 2 boxes. 2 boxes, right? You have your 2 piston box. Sorry, box with 2 piston containing box. from before. So each box A, or box 1, sorry, I called it box 1, didn't I? Sorry, box 1 has entropy S1, which is a function of U1, N1, and V1, right? The energy of the box, that sub-box, the number of particles in that sub-box, and the volume of it. And then box 2 has entropy S2 of its variables. Okay. All right, so each one has an entropy that we can maybe measure. And we can always say that the total entropy of the box, the system, is just the sum. Okay? So if we can measure the entropy of one and the other, then the total entropy is the sum. Really simple. That's one part of linearity. The other part of linearity is that, I'll show you. So the other one is that S, and, I'll call this A, right? And then there's B. The other property, which is that if you take entropy and you multiply each of its parameters by a constant lambda, it's just a number. Think of it 2 or 3 or whatever you want, right? So we're going to, I'm sorry, I erased that wrong. So if we're going to double the energy, double the volume, right? We're going to double everything and double the number of particles. Sorry, bad color choice. Right? Lambda is a number. Right? Just a multiplicative factor, right? We're going to make the box bigger, we're going to make it twice as energetic. Then all that happens is that the entropy of that enlarged box is just multiplied. So it's the original entropy multiplied by lambda. Okay, so if we double the size of the box, double the size of the number of molecules, and double the energy, then the entropy is just 2 times the original entropy. Really simple. It's just like a linear function. Mx plus b. All right, and there's 2 more properties that we have to mention, which is monotonic. Which all that means is that the derivative, sorry, let me write this carefully because we haven't done multiple derivatives yet. The derivative of entropy with respect to energy, right? How does the entropy change as you change the energy? Sorry, has the entropy change as you change the energy? Sorry, this is U. Sorry, not dE, but du. Is always greater than 0 for fixed N and V. Okay, so if we fix, so it's very simple. If we have a box that we fix the volume and the number of molecules, and we start pumping energy into it, then the entropy always goes up. It never goes down. Really easy. Okay, and one more thing. A single value. What that means is that we can always calculate its inverse. So if we can measure the energy as a function of N, V, and S, right? If S is our input, the entropy is our input, then we can always resolve this, rearrange, and resolve the equation so that it's now a function of the internal energy, not the entropy. Right? We can always go between these two. All right? So it just depends on our system. Maybe it'll be more useful to change the entropy of our system. We'll see a good example of changing the entropy of our system at fixed energy. For instance, things that not are at fixed energy and have varying entropies. And you can always rearrange it so that U is an input instead of S. Okay, so we can always talk about one or the other with respect to the other one. Okay, so we have a function that's always increasing. It's linear, and that it can either be a variable or the function itself. Okay, we can always calculate. If we know U, we can know S, and vice versa. So we can talk about all of these on equal footing. All right, and we know it's always increasing. It's always going to reach a maximum. All right. So what we're going to do is we're going to come back to our piston on Thursday and let the system evolve until entropy reaches the maximum, and then we'll find out where that piston sits. It'll become very obvious to you, and once we learn that, we'll be able to start thinking about, well, what if we have a system of known temperature or energy? How can we compare our system to that? Okay, and then we'll get temperature to come in. All right. So we're almost there. We're almost at temperature, and then we can start thinking about chemistry. All right. Have a good one, guys. See you Thursday.